Alright, this is on the common ion effect. The objective for this lesson is to identify the solubility of a salt and or the KSP value for the salt based on the concentration of the common ion already present in the solution. I'm going over a problem at the end of this presentation in order to help students who were struggling with the assignment on today. So I've received some feedback and I'm trying to create a video to help out a little. So quickly I want to review the pH and the pOH. How do we define the pH and how do we define the pOH? These are typically looked at for acids and bases, but I wanted to do a review very quickly before going into this presentation of the problems. How do we find the pH? The pH is simply a measure of the hydrogen ion concentration in the solution. So pH is the negative log of the concentration of the hydrogen ion. Typically we're going to measure concentrations in moles per liter, so that's going to be what we would place in the concentration of the hydrogen ion. For example, a concentration of 10 to the minus 5 would give a pH of 5. Now, how do we define pOH? pOH is the concentration of the hydroxide ion. And so pOH is going to be the negative log of the concentration of the hydroxide ion. And it's always important to remember that pH plus pOH is equal to 14. Now, the criteria for success for solving these KSP problems: first of all, you need to have a printout or access to the polyatomic ions worksheet, which is in the Google Classroom, a periodic table, and a printout of this CFS before solving or starting any problem. These sheets will help you to write the balanced equation for the solvation reactions of the inorganic salts. For example, if you don't know what polyatomic ion you're going to be looking at, for example, sulfate, carbonate, cyanide, this sheet will have a list of all the polyatomic ions that you can use for solvation. So you write the expression for KSP for the solvation reaction is the next step. Oh wait, I skipped a step, I'm sorry. You write the balanced equation for solvation of the solid into its ions, typically one cation and either one anion or a polyatomic anion. So in order to find out what the polyatomic anion is in the charge, you would look at your polyatomic sheet. Then you write the expression for the KSP for the solvation reaction. You do not include the solids, so this would just be the ionic product, the product of the ions with the subscripts as, the coefficients as exponents in the reaction. If the solubilities are given, you have to convert the concentrations into moles per liter because you do not want to use grams per liter when you are looking at the number of moles at equilibrium. Finally, use the ICE method to solve the equilibrium problem given. And that's it for the CFS. Now, here is a problem that's similar to problem 3. We're going to read this first. It's a 3-part problem. We have to answer all 3 parts. The KSP of silver sulfate, Ag2SO4, is 1.2 times 10 to the minus 5. Calculate the solubility in moles per liter of silver sulfate in water in 0.1 molar silver nitrate solution or in 0.2 molar potassium sulfate solution. First step that we're going to do is we're going to write our balanced equation. We know that silver is our cation and sulfate is our anion. This is pretty straightforward. And we see that we have 2 silver ions and 1 sulfate ion to balance the equation from the silver sulfate solid. Next, we're going to write the expression for our KSP. We're going to leave out the silver sulfate solid, because we said solids aren't a part of the equilibrium reaction, we're just going to have the silver ion and the sulfate ion. The silver ion has a coefficient of 2, so that's squared, and the sulfate ion has a coefficient of 1, so that's to the first power. And we aren't given any solubility, so we just have the value for the KSP, which is 1.2 times 10 to the minus 5th. Next, we prepare our ice table. Our ice table has, bounce up here, our ice table has an initial concentration of 0 for the silver ions, 0 for the sulfate ion. Now, in the event that there were ions already present, like if we had a solution containing silver or containing sulfate, then these initial values wouldn't be 0. But because there's no common ions present for water, the initial concentration of both of these are 0. And our change in concentration is 2x because of the 2 in front of the silver ion, and x because of the 1 in front of the sulfate ion. And we add 0 plus 2x to get 2x, and 0 plus x to get an equilibrium concentration of x for sulfate and for silver, respectively. Now, we know that the concentration, here I set up the problem, we have our KSP expression of silver squared times sulfate. We have our KSP value that was given to us of 1.2 times 10 to the minus 5. And now, because we set up the ice table, we know that our silver concentration ion is 2x and our sulfate concentration is x at equilibrium. And so we can use the ice problem method to solve this equilibrium problem by substituting for Ag, or the silver ion squared, with 2x squared, and the concentration of sulfate with x. And that gives us 2x squared times x, squaring the 2x, and remember we have to square the 2 as well, so that's 4x squared times x, which is 4x cubed, is our value for our KSP. But we know that the KSP is equal to 1.2 times 10 to the minus 5. So continuing with solving this problem, we now know that 4x cubed is equal to 1.2 times 10 to the minus 5. And solving for x, we just have to divide by 4 and take the cube root. And the cube root gives, and by solving for x, we get x is equal to 1.44 times 10 to the minus 2. Or, in your calculators, you would get 0.0144 molar. Now we go back to the problem. We're asked to read the problem, 3-part problem, answer all 3 parts. The KSP of silver sulfate is 1.2 times 10 to the minus 5th. And we need to calculate the solubility of silver sulfate in the following. We just solved for what the solubility, or x value, is for silver sulfate in water. Right here. Because water has an initial concentration of 0, and the change is 2x and x, and the equilibrium concentration is 2x and x. And so x, because we see here, that's the amount of Ag2SO4 that has dissolved in solution. And so the solubility of Ag2SO4 is 0.0144 or 0.0144 moles per liter.